Okay, now that you've seen the exploration, we know, and as I talked about in the video, the incenter is the name that we've given to the point of concurrency of the angle bisectors of a triangle. Okay, so if I draw in the angle bisectors of each angle of a triangle, okay, they all line up at the same point, which we call the incenter. That's that point of concurrency of the angle bisectors. Okay, so now we have our incenter theorem that I showed in the exploration as well. The incenter of a triangle is equidistant from the sides of a triangle. So since if P here occurs at the angle bisect, if P is the incenter, which we would need to have these notches to show the incenter, but if P is the incenter of triangle ABC, then the distance from P to each side, and if you notice that that distance, we actually have that perpendicular, because that's how we do that distance, then the distance from P to F is the same as the distance from P to E is the same as the distance from P to D. So all of these distances are the same because P is the incenter. Okay. So here in example 3, in the figure, the distance from N to D is 5x minus 1, so N to D, this distance. And the distance from N to E is 2x plus 11. We want to find x. Okay. Actually, no. Scratch that. I don't have the directions here. First, we want to find the distance from N to F. We want to find the distance from N to F. So N to F. So we're looking for this distance right here, N to F. But if you notice here, if we notice here at C, angle C, this line is the angle bisector of angle C. And this line here over at B is the angle bisector of A. And how we can tell that is by the arches, because these two angles are the same. So AN is the angle bisector, here CN is the angle bisector, and then BN is the angle bisector because of all these notches. So that tells me that N is the, gosh, guys, I'm having a tough time then, is the incenter. Is the incenter of triangle ABC. So since it's the incenter, then I know its distance from all the sides is the same. So the distance from N to F is the same as the distance from N to E, which is the same as the distance from N to D, because they give us that little 90 on all of those. So I know that NF equals NE equals ND by the incenter theorem. But we know that ND right here is equal to 5x minus 1. And that has to equal NE. And NE is 2x plus 11. So I now have an equation with two x's in it, so I can actually solve this for x now. Subtract 2x from both sides. Let's add the 1 to both sides. And then divide both sides by 3. So x is equal to 4. So we're trying to find the distance from N to F. But I don't know anything about NF, but I know, let's see, NE is equal to this guy. And x is 4. 2 times 4, 8, plus 11. That makes that 19. But NE equals NF, so that tells me that NF must also equal 19. Okay. All right. Next, construction. We have a construction, one more example, and then we're done. Okay. So now we're going to be inscribing a circle. If you remember from earlier in this, we circumscribed a circle. The circle went around the outside. Okay. Now we're actually going to put the circle inside. So the circle barely touches each side of that triangle. Okay. So this one is actually a little more involved because we need to find basically, here's our steps. First, we need to find the incenter. To find the incenter, we need to do the angle bisectors. Okay. So we have to find the incenter. To do that, we need to find the angle bisectors. You need to find at least 2 of them. Okay, but then once you have that, you need a perpendicular to draw your circle. You need that perpendicular to draw that circle, and then once you have the circle, then once you have the incenter and a perpendicular, then you can draw the circle. Okay. So first steps first, we need to do some angle bisectors. So I'm going to pick a couple angles here. So I'm going to start here with angle A. So I'm just going to kind of do that here at angle A. So if you don't remember how to do an angle bisector, we'll walk through that. First step, draw an arc through angle A. Arc of any size, doesn't matter. Okay, but you want it to intersect both sides. So I'm just going to draw a random arc through angle A. Okay, and then, so now I have these 2 intersection points. So now I'm going to put my center on that extra intersection point, draw an arc up here. Doesn't matter how big, what matters is that you don't switch it. And then come down to the other side, draw another arc, and then find that intersection point. So it intersects right here in this middle right there. Intersection point right there. So now, again, I'm going to color code this. I would encourage you to do this in pencil, but you can go ahead and highlight over and color code it. Okay. I'm going to then draw from A to that intersection point, and that is my angle bisector. Okay, so I've now bisected this angle. So this and this are the same. Okay, so now I'm going to come in and I'm going to do another one. Let's do angle C over here. Okay, again, I'm going to do that same thing. I'm going to come in, and a lot of times when I do this, I hardly move my compass. I just leave my compass at the same setting for the whole thing. So I'm going to come in, I'm going to draw that arc, and then here I'm going to mark these intersections so we can see it. We're going from this point to that point on that arc. So we're looking at this arc here. We're ignoring the previous arcs. We're looking at this arc here. So I put it here at this orange point, come out, draw an arc out here, and then come over to the other intersection point, draw another arc. Okay, so now it intersects at this point right there. Okay, again, I'm color coding. I'm going to use orange. Come in, draw the angle bisector here. This whole process was just us finding that incenter. So now we have it where the pink and the orange meet right here. We'll call this point D. That right there is our incenter. So now we found our incenter. Okay. Unlike the last construction, we were able to just go now, put it on D. Oops, sorry, I'm bouncy. Okay, and then stretch it out to a point and draw my circle. Okay, but I need to know. I don't know what point to stretch it out to, because I need a perpendicular distance from D to one of these sides. Okay, so I think I'm going to go from D. We pick one of the sides, doesn't matter which one. Let's do the perpendicular from D down to this bottom side right here, this A to C. Okay, so how to do that? I'm going to put my point at D. I'm going to stretch it out to just past my green, just past my bottom line, and I'm going to draw an arc in. Okay, if you notice, that arc intersects this bottom at 2 different points. It intersects it right here, and right here. Okay, at those 2 X's. X marks the spot. So now I'm going to come in. I'm going to put my point at that intersection, and I'm going to draw an arc down here, and then do another one from this intersection. See, I draw the arc down here, never, never land. And now I'm going to connect D down here to that. Again, I'm color coding, just so it's easier for you to keep track of the steps here, because this is slightly more involved. The whole purpose of doing this was to find this point. Oh, I'm a little off. You really don't want to be off on this one, so I'm going to move it over just a little bit. Okay, the whole point was to find this point right there. This point right here. That perpendicular. So now I know I'm going to draw a circle. So move everything out of the way so I can spin my paper. I'm going to put my center at D, stretch it out to this green mark we just found, and draw a circle. And if everything was exact, it should hit barely hit each side of my triangle, which, hey, did a pretty good job. There's my circle. See how it just touched each side of the triangle? So there is what we call an inscribed circle. Because an inscribed circle, up here, inscribed, let's highlight that word. Inscribing a circle, the circle just touches, each side of the triangle. Okay, it barely touches each side. Okay, right. So last example, this was the very last one and then we'll be done. A city wants to place a lamppost on the boulevard shown. Okay, so it wants to put a lamppost in this green area shown. So the lamppost is the same distance from all three streets. It wants it to be the same distance, which geometrically we'd say that's equidistant, okay, from all the streets. Should the location of the lamppost be at the circumcenter, or that should be in center of the triangular boulevard? Explain. Well, we want to be the same distance from all three streets. Those streets are really the sides. We want to be equidistant to the sides. To be equidistant to the sides, it would need to be at the incenter. So my answer would be here, incenter, because an incenter is equidistant to the sides of a triangle. Now, if I wanted to be equidistant to the intersections here of each street, like here, here, and here, then that would be the circumcenter, because the circumcenter is equidistant from the vertices. Okay. All right, go ahead and jot down your practice, and good luck.